Okay, good morning. It's time to get started with the lecture for today. I guess some of you were not able to make it today. Now there's some other conditions that are making it hard to come to class today. But we're gonna start with the new topic today. Please make sure that you turn off your computer screen and focus on this lecture. This is the last topic that we're going to cover before our first exam. The exam is going to be next week as we schedule. This next Thursday, you're going to have 75 minutes to work in the exam, and you will basically see a multiple choice questions on the first part, and then kind of problems that we've been discussing in class and also in the home. So we're going to talk in detail about the exam on Tuesday. We're going to go over the review and what topics are going to be covered in class in the exam. But other than that, do you have any questions about the exam or about the topics that we have covered? Yes, sir.
So the multiple choice is probably more like vocabulary definition.
It's going to be more focused on concepts. So, yes, for example, we discussed what the feasible region is. So you should know what the feasible region is and why the feasible region is important. We talk about the extreme points, why the extreme points are important. You know you're going to be able to find the solution or the optimal solution for your problem if you focus on the extreme points. That type of questions. Okay? Any other questions? So, so far in the class, we've been focusing on modeling the problem. So I'm presenting you with some problems that are common in manufacturing, common in production settings, and then you're being modeling these problems using linear programming. We also talk about one way to solve these problems, which is using the graphical method, right? But there was one limitation about this method, and I don't know if you remember what was the limitation about the graphical method. I have asked this question before. I was wondering if you remember. The graphical method, the only limitation about the graphical method is that you have problems that have only two variables. So remember, we were solving problems with x1 and x2, but if you take these problems, if you have more than two variables, then you're not going to be able to use the graphical method because you will need a three-dimensional space to search for your solution, and that's going to be very hard. So in order to find solutions for our problems that have more than two variables, now we're going to discuss the Simplex algorithm. Okay, so this method is going to allow you to search for solutions and find optimal solutions for linear programs that has more than two decision variables. So this is the learning objectives for the lecture. Use the Simplex algorithm to solve linear programming models with more than two variables. And you can find these topics in your textbook in section 3.1, 3.2, and 3.3. If you want to read about those topics, those are discussed in those three sections in your textbook. So the agenda for today, I'm going to provide an introduction of why we need to use or why the Simplex algorithm is important. Then we're going to talk about the basic stuff that you need to do before you apply this Simplex algorithm, how to transition from the graphical method that we learned in class to the algebraic solution and how that relates to the Simplex algorithm. Then we're going to talk about the Simplex algorithm itself. So the introduction, for the first 3 weeks in this course, again, we focus on two major things. The first one was the modeling of LPs, and the second one was solving these LPs that have only two decision variables. We're using the graphical method for x1 and x2. But in real life, we know that we have problems that have many variables, and a method is needed to solve LPs with more than two variables. So we will study the simplex algorithm, which will be used to solve these problems that have more than two decision variables. And now the topics that we covered at the beginning of the class, which were the linear algebra topics, are going to become very useful because the simplex algorithm used the Gauss-Jordan method to find the solutions. So if you remember, we went through the Gauss-Jordan method in class, and the reason for that was because we're going to use those elementary row operations to find our solutions in the simplex algorithm. So let's start by the basic stuff. So in order to use the simplex algorithm, we need to change our formulation to what we call a standard form. And what is the standard form? So again, the LP must be converted into a problem where all the constraints are equations and all variables are non-negative. So we talk about why it's important to have our decision variables are as non-negative, greater or equal to 0. But now we also need to find out why it's important to put these constraints in a equation form. So you remember in our formulations we were using to formulate the constraints in less than or equal or greater or equal sign. Now, in order to use the simplex algorithm, we need to make those less than or equal or greater or equal signs equations. So we want to make those signs equal signs. So an LP in this form is said to be in standard form. So we're going to make these inequalities equations. And when we get to that point, then we can say that our equations are in standard form. So what are the three steps? These three steps will depend on the type of constraints that you have. So for example, if you have a constraint with a less than or equal sign, and you want to convert that to an equation, you will have to add a slack variable, what we call a slack variable, and I'm going to be using S as my notation to denote a slack variable. And the sign restriction is I greater or equal to 0. Now, if you have a constraint with the greater or equal sign, then if you want to convert that into an equation, the equal sign, you're going to subtract an excess variable, and I'm going to use E to denote this excess variable, and the sign restriction, again, greater or equal to 0. So two different cases, one for less than or equal, and the other one for greater or equal. Now, we can also have variables with unrestricted signs. This variable can get values with negative value or positive values. So that's what we call an unrestricted sign variable. So you can replace that variable using this xi prime minus x double prime I into your formulation, and then make these two new variables greater or equal to 0. And we're going to see how this applies with some examples. Okay, so three different cases. One for constraints with less than or equal, one for constraints that have greater or equal, and then the case in which you have unrestricted sign for your decision variables. So let's look at this example. We have leather limited manufacturers, two types of belts, the deluxe model and the regular model. Each type requires 1 square of yard, so that's the restriction in terms of the material. Then we have the restriction in terms of the labor hours that we have available. So the regular belt requires 1 hour. This deluxe belt requires 2 hours. And each week we have 40 square yards of leather and 60 hours of skilled labor. So we have two restrictions, one for the labor and one for the material. We know the requirements for each type of belt, and we have two types of belts. And we also have the information in terms of how much profit you made for each type of belt. So $3 for regular belt and $4 for deluxe belt. So we're going to formulate this problem. We want to maximize our profit. We have two constraints. In our decision variables will be how many of each type of belt you want to produce. So in terms of the decision variables, again, as I mentioned, you have two decision variables that are related to the type of belt that you're going to produce. So we can have X1 and X2, which are the number of deluxe belts produced weekly, and X2 is the number of regular belts produced weekly. We know the profit that you make for each type of belt. So X1 is related to the deluxe belt. You make $4, and for X2 is the regular belt. You make $3. So your objective function is to maximize the profit that you're going to make by selling those belts. We have a constraint for the material. So for each type of belt, you have a yard of material, and you have a constraint in terms of the material that you have available. That needs to be less than 40. And also you have a constraint for the labor hours. You have 60 hours per week, and you know that the deluxe belt will take 2 times the time that it takes for a regular belt. And you have your non-negativity decision variables. So this is our formulation. Okay, so this is something that you already know how to do. You know how to formulate a problem. This is a two decision variables problem. But what we want to focus using this example is to make these constraints. We want to make those convert that problem into the standard form. Okay, so to convert the labor and labor constraints to equalities, we define for each constraint a slack variable. Why do we need a slack variable? Let's see if you are understanding what we're trying to do. So if we want to make this an equality, why are we using a slack variable or not an excess variable? So remember, we have an inequality in this form, less than or equal. So what we discussed here is that when you have a constraint in this form, less than or equal, and you want to convert that into an equal sign or equality for your constraint, then you're going to add a slack variable. So that's the reason we're going to add this slack variable. We want to make that constraint an equality. And since the sign of that constraint is less than or equal, we are adding this slack variable. If instead of having a less than or equal, you had a greater or equal, then instead of adding that slack variable, then you were going to subtract the excess variable. But in this example, we only have less than or equal constraints. So we define for each constraint a slack variable, and in this case, the slack variable is the amount of resource unused for each constraint. Okay, so if you don't use part of the constraints, so what we are doing here is the following. We want to make that an inequality. So we have x1 plus x2 plus s1 equal to 40. If you solve the problem now when you have this constraint, x1 and x2 can have any value that is less than or equal to 40. So this could be 10 and this could be 10, and the constraint is going to be satisfied because 10 plus 10 is going to be 20. And that is going to be less than or equal to 40. But what will happen if instead of that, this sign
instead of being less than or equal, if this sign was an equality and this was 10 and this was 10.
Will that constraint will be feasible? No, right? Because 10 plus 10 is 20 and that is not equal to 40. So for that reason, we need to add this slack variable, because if this is 10 and this is 10 and we have the constraint in equality form, then this slack variable is going to assume the rest of the numbers or values that you need to make that inequality. Okay? So remember, what we're trying to do now is we want to set up the problem in such a way that we can use the simplex algorithm. That's the only reason that we are adding these decision variables, slack variables. We want to make this equality, these constraints equality, so we can use the simplex algorithm. So that's why we need to add these decision variables so we can form these equalities and we can transition to the algorithm. Okay? So that's the reason for adding that slack. So now we want to put this problem into standard form. So we're going to change these constraints as we explained. So we're going to have, for the first constraint, we have x1 plus x2 plus s1 equal to 40. And for the second constraint, we're going to use a different slack variable, but we'll still make this constraint an equality. So we have 2x1 plus x2 plus s2 equal to 60. And now we want to make these decision variables positive. So in order to make that positive, we have to make this x1, x2, s1, and s2 greater or equal to 0. And now we have our problem in our formulation in standard form. So you make those constraints that were inequalities, you are making them equalities by adding those slack variables. Any questions? Okay. Yes, sir.
Are slack variables applicable in any
What you mean in terms of the signs of the constraints, or
just like anything for just like a safety or access or
yes, I mean you can use these slack variables to model different things. Like if you want to know, for example, if you're gonna have a production schedule to meet, and you know that you're not gonna be able to fulfill the demand, and you want to know how many units are gonna be behind or they're not gonna be able to satisfy, a slack variable is gonna tell you that. So that's in terms of the real problem. But yeah, it can have multiple, could be useful for different things. But the important thing to remember here is that you only use slack variables when you have less than or equal constraints. In case you have greater or equal, then you use the excess variable. And then we have another example here. Yes. So you remember this problem? This was the problem for marketing purposes. We were trying to find out what was the best way to promote this announcement in football commercials or comedy type shows commercials. And this is the Dorian outer problem. And this was the formulation that we discussed in class. So you remember we had these greater or equal constraints that were basically you wanted to at least get to 28 million women and 24 million men with this commercial. So at least means that you want to have that lower bound, and that's the reason we were using these greater or equal constraints. But now we want to make this problem or change this problem to a standard form.
And as we discussed, when you have greater or equal constraint, now instead of using a slack variable, you're going to use an exit variable. And you're going to subtract that variable to your constraint. So in that case, we start with our objective function, minimization of z equal 50 x1 plus 100 x2. We have our first constraint, 7x1 plus 2x2, and 2x1 plus 12x2. And now we want to make this inequality equal 28 equal 24. But since this is a greater or equal constraint, instead of adding a slack variable, we're going to subtract a exit variable. And if you apply the same concept that we explained when you have, let's say here, if you have 10 and 10, use 10 because it's an easy number to compute. So if you have 10 and 10 here, then you're going to have 70 plus 20, that's going to be 90, and that will satisfy your constraint, right? But in the case that this becomes an equality constraint, if this becomes an equality, then you know that your constraint is not going to be satisfied because 90 is not equal to 28. So that's the reason we add this excess variable. So when you subtract that E1, then you're going to subtract 62. That's going to be equal to 62. And then your equality will hold. Because 90 minus 62 is going to be equal to 28. Okay? So we are, again, using this excess variable. So when we have a constraint that is an equality, we are able to satisfy that constraint. Okay? Any questions? And remember, again, the objective, what we're trying to achieve now is we want to transition from this formulation that we know already how to formulate. We want to make that formulation into a standard form so we can apply the simplex algorithm to solve the problem. So I'm going to give you a chance to practice what we just discussed with this problem. So I want you to put this problem into the standard form. So just take a couple of minutes and try to make this a standard form problem. So here we have a combination. We have less than or equal constraints, and we have greater or equal constraints. how many slack variables are you going to need? Yes, you need 3. And excess variables? Just 1, correct. So you're needing 3 slack variables for the first 3 constraints. So x1 equal to 100, x2 equal to 100, then 50 x1 plus 35 x2 equal to 6,000, and 20 x1 plus 15 x2 equal to 2,000. Something that you need to remember is that you're going to use a different slack variable for each constraint. So in this case we have 3. We need 1 for the first one, it's 1. 1 for the second one is 2, and 1 for the third one is 3. And then we have minus the excess variable 1. Are we done? There's one thing that is missing. Anyone remember? The non-negativity constraints for the decision variables. So we have x1, x2, s1, s2, and e1 greater or equal to 0. Oh, yes, and s3. Okay, so that's how you change the original LP to a standard form. There's one more thing that we need to discuss, and it's the case in which we have a unrestricted sign decision variable. And for that I have an example here. Let's say we have a baker has these many ounces of raw material and 5 packages of yeast. Then we know the requirements to baking a loaf of bread. It requires 5 ounces of flour and 1 package of yeast. And each loaf of bread can be sold for these 30 cents. And we have 2 options here, depending on what happened. If we need more material, we can purchase additional flour for 4 cents per ounce. But in the other case, if we have some left over, then we can sell that leftover at the same price. So depending on how many are you gonna bake, you can have 2 options. You might end up having some left over, or you can actually purchase more material depending on how many are you going to produce. So the problem is asking to formulate an LP that will help this baker to maximize the profit. Okay, so we're going to formulate this problem. Anyone have an idea of what decisions need to be made in this problem? What are our decision variables? Yes, you have the number of ounces of flour that you're gonna buy or you're gonna sell, and also you have another decision variable. How are you gonna make profit? Yes, by selling this bread. Okay, so you have another decision variable, number of loaf of bread baked. Those are the ones that you're selling, and you also have the number of ounces which flour supplies is increased by cash transactions. So remember, X2 can be if you sell or if you buy. It could be you can go on both
directions. So if you formulate this problem, then this is your formulation. You're trying to maximize your profit. You know, if you sell these loaf of bread, you will make 30 cents per unit. But also if you buy more material, then you know that you have some cost. But that also can be a positive or an increase in your revenue if you end up selling the leftover. So that's what is interesting about this problem, because that X2 is unrestricted. It could be positive or negative, depending if you sell or if you buy the raw material. Okay? So, as a note, we have here X2 will be greater than 0 if you purchase this raw material. And it does make sense here, right? If you buy, that X2 is going to be positive and it's going to subtract to your revenue because you're spending, you're buying material. But if you sell the leftover, then that will be a negative value, making your revenue, this portion here of the objective function, positive. That will increase your revenue. Now, in terms of X2 equals 0, that means that the flour was bought or sold. There was nothing happened. You just used the material that you had available. So this decision variable, X2, can have different values that could be positive or negative. And if we want to formulate this linear program into a standard form, we need to take that into account. And if you remember from the beginning of the lecture, let's see if this link works. It's not going to work. So if we remember here, when the variable is unrestricted inside, we can replace that variable in the objective and in the constraints with this difference of the same value. So we're going to have x prime minus x double prime of the same variable. And that will help us to formulate our LP into a standard form. And you'll see how now. So if we go back to the example, having some technical difficulties. Yeah, I apologize for this. It's the first time that happens. Okay, so if then remember that we have X2 that is unrestricted, so we're gonna
change that decision variable x2 to x2 will become x2 prime minus x double prime 2. And we're going to use that decision variable, that difference, as our decision variable in our problem. So we're going to have max z equals 30x1 minus 4x2 prime plus 4x2 double prime, subject to 5x1 minus x2 prime plus x2 double prime plus s1 equal 30, and then we have x1 plus x2 equals 5, and we have our non-negativity constraints. Yes, sir. Because you're taking that and you're putting it in here, and you have a negative sign in front. So when you multiply that difference, x2 will become negative and the other one will become positive. That's a good question. So later in this course, you will see how would that work out. But for now, I just want you to focus on changing the original LP to a standard form and know how to do that transformation. So we can transition to the either, which is the Simplex method. So let's transition from the graphical solution to the algebraic method or the algebraic solution. So the development of the algebraic simplex method is based on the ideas conveyed by the graphical LP solution. And you'll see how the solutions and how the methods is related. So in the graphical method, the solution space is the intersection of the half spaces representing the constraints. So remember, we have this two-dimensional space. We were drawing the constraints in the graph, and we were finding the feasible solution. And we knew that in the feasible solution, we can find an optimal by drawing these isocost and isoprofit planes and moving those planes in the right direction. So in the simplex method, the solution space is represented by the simultaneous linear equations and non-negative variables. Okay? So we're going to be using the linear equations, the ones that we're plotting into the graph to draw the constraints. And we also we're going to be finding which are the non-negativity values. So in the algebraic solution space, defined by the number of columns times the number of rows, times the number of columns, basic solutions corresponds to the corner points in the graphical solution space. And they are determined by setting the variables equal to 0 and solving the equations for the remaining variables. So our basic variables or basic solutions are going to be telling us that once we find these basic solutions, those are our corner points in our graphic method. So if you remember from the graphical method, we're drawing these constraints and we were determining our feasible region. So let's say this was our feasible region. This is x2 and x1, and this is constraint 1 and this is constraint 2. By drawing those constraints, we found that this is the area that both constraints were satisfied. And then we noticed that our optimal solutions were always found in these extreme points. Unless we have an isoprofit line, then when you move that line, it's parallel to one of the areas of the feasible region. In that case, when you move that, then the optimal solution will be of the solutions on that line. But if that was not the case, then you remember that when you draw that line, if you move, it's going to be the last point that touches the feasible region. But you always know that it's going to be an extreme point. So what we're saying here, if we find these basic solutions, we are going to be finding the corner points of our feasible region. So this means that the maximum number of corner points is, we can find that number by using this expression. Okay. Again, n is the number of rows and the number of columns for your system of linear equations. And this figure basically compares the graphical method with the algebraic method and tells you how they relate. So we can go through it. In the graphical method, there are all the constraints, including the non-negativity restrictions. This is what I'm showing here. And the solution space consists of infinity of feasible points. Solution space is the feasible region. So here you can have an infinity number of solution points. Okay? All the points that are in here are solutions. That doesn't mean that they're optimal. If you are looking for the optimal solution, then you know that it's going to be located in one of those extreme points. Okay? The algebraic method represents the solution space by m equations, the linear equations, in n variables, and restrict all the variables to non-negative values, m less than n, and the system has an infinity of feasible solutions. Again, those solutions, those basic solutions, relate to the corner points of your graphical method. Then, second thing that you do in the graphical method is to identify the feasible corner points of the solution space. So we identify those points. The candidates for the optimal solutions are given by infinite numbers of corner points. So again, we know that the optimal solution is one of these points. In the algebraic method, we determine the feasible basic solutions of the equations, and those correspond to those corner points in the graphical method. And the candidates for the optimal solution are given by a finite number of basic feasible solutions. So as you can see, those two methods are related. And we use the objective function in the graphical method to determine the optimal corner point from among the candidates. So remember, we were drawing this isocos, this blue line, isocos or isoprofit line, using the objective function. And then we move that line that is coming from the objective function in order to find our optimal solution. So that's what this box here is telling you. So you use the objective function to determine the optimal value or the optimal solution for your problem. Now in the algebraic method, you also use the objective function to determine the optimal basic feasible solution from among all the candidates, and we're going to see how that works out with the method. Okay, so it's the same thing, but you're going to be using a different strategy to find the optimal solution when you have multiple variables, or more than two decision variables. So consider the following LP with two variables. This is the feasible region is in gray. So that's shaded area is your feasible region. And the graph is telling you this is your optimal solution. But we're going to use this to transition to the algebraic solution. So we have the constraints. These constraints are here. Those are graphed in this area. And we want to see how can we solve this problem using the algebraic method. So the first thing you're going to do is to take those constraints that are inequality and you're going to put them into an equality form. So that's what we're doing here. So the algebraically, the solution space of the LP is represented by the following equations and variables. So now you're adding those slack variables and you are making those equality. Okay, so we're going to have two slack variables because we have two less than or equal constraints. And we also have the non-negative t decision variables, so greater or equal to 0. Now, we need some basic solution. And the basic solutions are determined by setting the number of rows minus the number of columns. And in this case, we have two equations. So that's going to be our number of rows, that's m. And we have 4 decision variables. So n equals 4. Those are decision variables. M is the number of linear equations that you have or the number of constraints. So when you subtract those, then you get 4 minus 2 equals 2. And those two variables equal to 0, and solving for the remaining, we have n equals 2 variables. So for example, if we set x1 equals 0 and x2 equals 0, the equations provide the unique basic solution equals to x1 equals 4 and x2 equals 5. So we make these two decision variables equal to 0, x1 equals 0 and x2 equals 0. Then you know this is going to be 0, and you're going to end up with a basic solution in which s1 equals 0, s1 equals 4 and s2 equals 5. And we can map that point into our graph. So these solutions corresponds to point A in our graphical solution. Let me go back to that graph. So the point in which you have x1 equals 0 and x2 equals 0 is this point. Okay? So with the algebraic method, we're going to be finding these basic variables, and we're going to be moving from here to here and find out if that is your optimal solution. Or we can also move from here to here, find out if that's your optimal solution. If that's not the case, then you can move from here to here. That's what we're going to do. We're going to be moving from point to point until we find the optimal solution. Okay, so another point can be determined by setting x1 equals 0 and s2 equals 0. And that will result in these two equations. So if you make those two equal 0, then you have 2x1 plus x2 equals 4, x1 plus x2 equals 5. The associated basic solution is x1 and x2, x1 equals 1 and x2 equals 2. So if you plug in those values into those two constraints, then you will get those constraints are going to be satisfied. And you know how to solve for those in order to get those values. We can also map that point to one of the corner points in our graph. So let me just show you that really quick. That's point C. x1 equals 1, x2 equals 2. So that's this point.
And at this point, you probably are wondering which of the variables you need to set up equal to 0 in order to get a specific corner point. So we just plug in those values, and we found one corner, and then we found another area or another point in the area. Without the graphical solution space, we cannot specify n minus m 0 variables associated with a corner point. So the solution is the following. Consider all combinations in which variables equal 0 and solve for the resulting equations. So we can find all these combinations and solve for those equations. The optimal solution is the feasible basic solution, or the corner point with the best objective value. So if you're maximizing, it's going to be the largest positive number or solution. If you're minimizing, it's going to be the minimum or the smallest value. Non-basic variables are the n minus m variables or the 0 n minus m variables. So those values in which we have 0, those are our non-basic variables. The ones that are non-zero are our basic variables. So it's important for you to recognize between basic variables and non-basic variables. The remaining variables are called the basic variables. So non-basic and basic variables. And the solution obtained by solving the equation is referred to as the basic solution. So if you solve, let's say you make two of the variables equal 0, and then you obtain two values for the other two variables, that solution in which you have 2 equal 0 and 2 equal to a specific value, that's called the basic solution. You're going to have non-basic and basic solutions in your basic solution. Any questions up to this point? No is a lot of new things that you're learning today, but you'll see why those concepts are very important by the time we should start applying the simplex method. The method, the algorithm, is very mechanic, but in order for you to understand what's going behind that algorithm, you need to understand this concept. And it's very important for you to understand what's going on behind the solution. Because this simplex algorithm is the method that is used by, for example, Excel. If you put this model into Excel, Excel has already the simplex algorithm program. So we'll find the optimal solution for you by using the simplex algorithm. Same thing for simplex, same thing for other softwares that are available for you to solve these type of problems. Okay? So by learning this concept, you're understanding what's going on into the algorithms that are used by these softwares. So we have, consider the following LP with two variables. So we have our LP one more time. And we can basically list all the solutions for this problem in particular. So when we let x1 and x2 being the non-basic variables, x1 and x2 are going to be our basic variables. The basic solution is 4, 5, and that is associated. These are the values for x1 and x2, and the associated point in which you have x1 and x2 equals 0 will correspond to this point, which is A. And this is feasible? Yes. It's part of the feasible region. But when you have the objective value for that point, x1 equals 0, x2 equals 0, the objective function value is 0. Okay, so we have A here. And the objective value for A is 0. Now when we let the non-basic variables, or these two values being equal to 0, then our basic variables are x2 and x2. And those values for those variables are 4 and minus 3. That value is going to be located somewhere here. Is that part of your feasible region?
So I put the value or plug that value here. It is 4 minus 3. So it's in this quadrant of the graphical of the graph. So this point is outside what you call the feasible region based on your constraints. So what happened? That solution, even though you're plugging in you're following this strategy, you sometimes will get some of the values that are not feasible. So is this point feasible? No. So you have no objective value. Let's do one more. Maybe let's do the last one. So when you let S1 and S2 equal 0, then the basic variables are x1 equal 1, x2 equals 2. That point is this one. If that point is feasible, yes, it is part of the feasible region. It is actually this corner point. So Z, yes. And that point gives you an objective value, objective function value equals 8. That's your last point. If you look at the objective value here, you look at this column, you are maximizing. So the largest value from this list is 8, meaning that your optimal solution is going to be point Z. So you have found the optimal value or the optimal solution for your problem. So that means that x1 equals 1 and x2 equals 2. Any questions? So by listing, you look at the number of constraints, you look at the number of decision variables, including the flag variables or the access variables. You look at those numbers, then you find the difference between n minus n. That will tell you how many basic variables are you going to have. And if you want to find an optimal solution by using that information, you can start listing the non-basic variables by assigning them 0 values and start solving for the remaining variables, which are which are your basic variables. And the solutions that you obtain are your basic solutions. Then you need to find out if those points are feasible. If they are not feasible, then you don't have an associated point in your feasible region. But if they are feasible, then you can find out what is the objective value. And from the list, if you are maximizing, you find the largest value. That will be your optimal solution. Okay? But we don't want to go through this process every time we want to solve a problem. And right now it's very easy because we only have 2 basic values, 2 decision variables. But let's say you have 10. Can you imagine making all this process, trying to solve for 10 variables and so on? It's going to be very hard. So that's why different methodology is needed to find the optimal solutions for these problems. And that's where the simplex algorithms come into play. So now we're going to use all these concepts that we learned. We know how to do the Gauss-Jordan method. We know how to formulate the problem. We know how to identify a basic variable, a non-basic variable. We know how to change our problem to a standard form. So all these concepts are needed for you to understand the algorithm. So let's talk about the simplex algorithm. So as you can see now, the general form for an LP, suppose that an LP with n constraints and n variables has been converted into a standard form. You know what the standard form means. All the constraints are in equality form. Okay, so we no longer have any inequalities in our constraints. We only have equalities. Okay, so we have our LP into a standard form. The form of such an LP should be formed. Such an LP will be this one. So you're going to have all your constraints in equality form, and you're going to have your objective function and also your non-negativity constraint for the decision values.
Now, remember these matrix? We're using these matrices for the Gauss-Jordan method. Okay, so what you're going to do now is we're going to take this LP formulation, and we're going to transform that into this. We're going to use those matrices to apply the algorithm. Okay, so the constraint may be written in the system of equations of A times X, charge of decision variables equals B, your right-hand side. Okay? So consider a system of A times X equals B of linear equations in n variables. A basic solution to this system of equation is obtained by setting this number of variables minus the number of constraints equal to 0 and solving for the remaining n values. So this is what we did with the previous example. We're finding the difference, we were assigning 0 to those non-basic variables, and we were finding the optimal or the solution for the basic value. Also, this assumes that setting this difference of variables equal to 0 yields a unique value for the remaining n variables. So assigning these 0 values to your non-basic will yield a unique solution for the basic value. Okay, so if you're missing this explanation, if you're going outside the classroom doing the explanation, you're not going to understand what we're trying to achieve here. So I really encourage you to stay in the classroom unless you have an emergency, and to refer back to the first day of classes to remember those rules that we discussed in class. Okay, we want to avoid interruptions, and we want to keep environment that is good for your classmates to learn. Okay, so to find a basic solution to this system of equations, we choose a set of n minus n variables, which are the non-basic variables, or I'm gonna use this NBV to avoid writing this whole thing every time we need to refer to non-basic variables. So this notation will basically refer back to this. So make sure that you understand what NBV is, and set up each of these variables equal to 0. Then we solve for the values of the n minus this number of non-basic variables, n minus m, and that will be equal to n variables. So we're going to solve for this number of variables, which are the basic variables, or DV, that satisfy the linear equations that we have as constraints and our objective function. Then we know that different choices of non-basic variables will lead to different basic solutions. And from these basic solutions, we're going to find the one that is the optimal one, and that's going to be our solution. Okay, so this is going back to what we explained with the example. This is just in general words, but if you refer back to the example, what we're trying to do is just put into words what we did. So consider the basic solutions to the following system of two equations. We have x1 plus x2 equals 3 and minus x2 plus x3 equals minus 1. So now we want to know how many non-basic variables are we going to have. So we have 3 decision variables, x1, x2, and x3, and we have 2 equations or 2 constraints. So how many non-basic variables are we going to have? It is n minus m, which is equal to 1. So 3 decision variables and 2 constraints. Okay? So setting, for example, our non-basic variable, let's say we want to make x3 our non-basic variable, and the other 2 are going to be our basic variables. Then
x1 plus x2 equals 3 because we are making x3 equals 0. And we're going to have negative x2 equals minus 1. So that's a simple example that you can solve easily. So you know x2 is going to be equal to 1 from this second equation. And if you make x2 equals 1, then you can solve for x1 that's going to be equal to 2. So we can obtain this value from these basic variables by setting x3 equals 0, solving, we find x1 equals 2 and x2 equals 1. By simple making non-basic variable x3, making that equal 0, then we can find a solution for x1 and x2. And that gives us our first basic solution. Okay, so again, identify the number of non-basic variables, get one of those non-basic variables and assign a value of 0, solve for the other two, you get a basic solution. Okay, so we found our first basic solution. Now we can repeat the process. If we assign x1 as our non-basic variable and basic variables x2 and x3, then we have another basic solution. If we repeat the process with x2, we have another basic solution. The only difference that we're between these solutions is the assignment of the non-basic variable. So we started with x2, with x3, then we use x1, and then we use x2. So right now we have 3 basic solutions. And that's for this problem. 3 basic solutions for this problem. Now, some sets of n variables do not yield a basic solution. So if we consider the following system, if we let the non-basic variable equals 3, then we're going to have x2 and x1 as our basic solution. So x3 is going to be 0, and we end up with this linear system of equations. If you try to solve that problem, or if you're trying to find a value for x1 and x2 that satisfy those constraints, it's not possible. So since this system has no solution, there is no basic solution corresponding to this group of variables, or this having x3 as our non-basic and x2 and x1 as basic solutions. So that's something else that can happen. So any basic solution in which all the variables are non-negative is called a basic feasible solution, or BFS. Okay, so we can find our basic feasible solution by finding a basic solution in which all the variables are non-negative. So for the previous examples, x2 equals 1, x2 equals x1 equals 2, and x3 equals 0, and these other ones are basic feasible solutions. However, this fails to be a basic feasible solution because x3 is negative. And what that's telling you from the graphical method is that this solution is not feasible, so it is not part of your feasible region. Okay? So all these concepts, again, are what's needed in order to work with the simplex algorithm. And I've been talking about this algorithm over and over again. We will get to that point soon. So one more thing that you need to understand is the concept of adjacent basic feasible solution. So for an ALP with n constraints and n variables, two basic feasible solutions are said to be adjacent if their set of basic variables have n-1 basic variables in common. So if you look at the basic variables for your basic solutions, and you find that there's some of them that have one of those variables in common, that means that they are somehow close. Meaning that if you are at this point, and you're sharing one of the decision variables or one of the basic variables, then that other point will be here or here. Okay? So that's what this is telling you. Note that two basic feasible solutions are adjacent if they both lie on the same edge of the boundary of the feasible region. Okay, so that's what I just explained. So they are somehow connected with one of the constraints. And that is important when you start searching for the optimal solution, because you can start moving on the right direction to find your optimal solution. So if you move in this direction and you're improving your objective function, then you can move in this direction. You don't want to go back, and so on. So for example, in the leather limited LP, the basic feasible solution corresponding to point E is adjacent to the basic feasible solution corresponding to Z. So these 2 points are the ones that we are talking about. These points share n-1 basic variables. They share x1. And point E, it has the basic variables x1 and x2, and F, basic variable s1 and s2, are not adjacent. So we have E and F, since they don't share any basic feasible variables. And if we go back to the table that I showed you for that solution, I actually have that table next. This is what I'm talking about. So we have E and Z. E is here, Z is here. If you look at this table, the basic variables, they are sharing x1. Even though these are different, they're sharing x1, so that's why they are adjacent. So, the general description of the simple algorithm solving for an LP is maximization problem. So these are the steps for the maximization problem. These are the steps that we're going to follow in order to work with the Simplex algorithm. So the first thing you're going to do is to find all basic feasible solutions to the LP. Then we will call this the basic feasible solution of the initial basic feasible solution. In general, the most recent basic feasible solution will be called the current basic feasible solution. So at the beginning of the problem, the initial is going to be the current one. So we're going to start with 1. That's going to be our initial solution. Second step is to determine if the current basic feasible solution is the optimal solution. So once you find this solution, is this the optimal? If that is the optimal, then you are done. You found your solution. But if not, then you need to find an adjacent basic feasible solution that has a larger Z value. And the algorithm is going to tell you, by just looking at the tables, you're going to find out if that is the optimal solution or not. Then you're going to return to step 2, using the new basic feasible solution as your current basic feasible solution. So we're going to start, we're going to find our initial basic feasible solution. Then we're going to move here. If that is the optimal value, then we are done. If not, we need to find an adjacent basic feasible solution. Find out if it has a larger value. That's the case. Then you return to the step 2 and repeat the process. Okay, so I think I'm going to stop here I would like you to go over the material that we covered today. So when we start discussing the algorithm on Tuesday, you have a better understanding of what we're going to do. So on Tuesday, we're going to have the algorithm. We're going to start with the algorithm right away. And we're going to work on some examples. Just make sure that you understand the algorithm, what's going behind it, because from this point, from this algorithm, we're going to be expanding out to our other solution methods, but all of them are going to be based from this one. So if you don't understand this one, then you're going to have trouble understanding the other one. So again, this is very important. So, yes, sir.
The Simplex algorithm field
It's going to be up to here. So the Simplex algorithm is not going to be part. Yes, because the exam is on Thursday. Yes. But we're going to discuss the Simplex algorithm Tuesday. Okay? But all the material that we cover up to today, feasible solution, basic variables, and so on, is going to be part of the exam. Okay? Yes, on Tuesday, we're going to spend some time explaining the algorithm, and then I'm going to have about 20 minutes for explaining the format of the exam, the topics that are important, and to clarify any questions that you might have at that point. Yes, sir.
Are you going to post built-in slides?
Yes, yes. I'll do that today, so you have all the notes that you need for study for the exam. Yes. And also I'm going to post the video for today's lecture, so if you want to watch it. Any other thing? Okay, so I'll see you on Tuesday. And if you need to see me, I'll be in my office this afternoon, from 3 to 5.
Are you holding office hours at the beginning of next week? Monday, Tuesday, office hours?
Tuesday I will have office hours for sure in the afternoon, but if you need to see me outside the office hours, send me an email and we can.
Okay, because I have some questions about formulating LPs and stuff like that.
Okay.
I think it's stuff that I missed in that week that I was going.
Okay,
Alright.
no problem. Yes, sir.
There's the homework that was emailed.
Okay. Okay. Good. Thank you.
Thank you.
Excuse me?
You don't put project management.
The test? We'll talk about that. It's not gonna be next week for sure. It's the week after that. But I'm gonna adjust the material that is gonna be covered in the exam. No, we didn't have class this morning, so that will affect the material. Okay.
All right, look forward to it.
Yeah, I emailed you this morning. I know you
Right.
emailed me. Yeah.
Yeah,
So
pertaining to that.
yeah. So every time you get a university, you just follow the instructions.
I wasn't sure, like, 'cause I was at the bus stop and I was just like,
Yeah. No. If they say there's